everybody. So today we are doing 5-3 exponential functions, day 3. We're more looking just at exponential growth and decay. So exponential growth is what is on the left side. Looking at this, how would you describe this function? Is it increasing or decreasing? So as we go from the left to the right, it's going up. So this function is increasing. The base is positive. Okay, the next one. This function is, well, if I look from the left to the right, it's going down, so it is decreasing. The base would then be negative. Okay, so real-world applications. Exponential functions often model real-world growth and decays, the spread of viruses, for example. Exponential growth and exponential decay functions model quantities that increase or decrease by a fixed percent during each time period. The old way that we would model exponential functions is y equals a times b to the x. Given an initial amount a and the rate of increase or decrease r, the amount a of t after t time periods is given by, well, we're going to write that it is a parenthesis 1 plus r to the t. So one more time, a to the 1 minus r to the t. So if you look here, this plus sign means it's going up, so growing. This minus sign means it's going down, or it is decaying. So that's the easiest way to remember. If you see that it says growth, you are adding. If you see that it says decay, you are subtracting. Okay, so looking at this, find 1 plus or minus r. So let's go ahead and look at this. I have 1 decay of 10%. So that means I'm going to subtract it, because decay means subtract. And 10%, well, as a decimal, that's just 0.1. So what is that actually? It's just going to become 0.9. Now, my function. Very first thing I'm going to do is take my initial population. That is what A is, okay? So A equals initial. So whatever my initial amount is. So I have 3, 1, 2, 3 times 0.9 to the t. Okay, looking at this last one, we want a of 5. So I'm going to do 3, 1, 2, 3 times 0.9 to the 5th. That answer is going to give me 1845.28. Okay, so looking at this next one, we have a growth of 6.1%. So that tells me I'm going to have 1 plus 6.1%. What is that as a decimal? That's 0.061. So my final answer is 1.061. My 12 times 1.061 to the t. Now plug in 5 for t. When we plug in 5 for t, we should get 16.13. Okay, so let's go ahead and try the next one. Decay of 0.5%. So that's 1. Decay means minus 0.5%. Well, that as a decimal is going to be 0.005. So my final answer is going to be 0.995. So I have my initial population is 10 times 0.995 to the t. Now we're going to plug in 5 for t. So 10 times 0.995 to the 5th power, that should give me 9.752. One way you can also double check this is the fact that it says decay, and we know that means it goes down. Look and see. We started with 10, we got 9.752. Did that go down? Yeah, it did. So that is what we were looking for. Okay, so go ahead and try out the very last one on your own. Okay, so a to the 5th, you should have gotten 778. 0.55. So go ahead and just double check to see if you did the same work I did. Okay, so looking at this next one, we are determining the rate. So I know that 1.05 is equal to 1. Is this above 1 or less than 1? It's above, so it's 1 plus r, okay? So looking at this, let's go ahead and subtract that 1, so minus 1, so 0.05 equals r. So that would be my rate, or I could say it is a 5% growth. Okay, so looking at this next one, is that greater than 1 or less than 1? It's less, so I know that I'm doing a decay. So I can say I have 1 minus r equals 0.57. Let's subtract 1, so negative r equals negative 0.43. Get rid of those negatives, so r equals 0.43, or we can say 43% decay. Okay, go ahead and try this next one on your own. So we should have gotten 1.5% growth. The reason that I know this is because 1 plus r, 1.015, subtract the 1, so r equals 0.015, or 1.5%. Go ahead and do this very last one. Okay, so this is less than 1, so I know it's a decay. And then I have 1 minus r equals 0.975, minus 1. Negative r equals negative 0.025, or r equals 0.025, which is the same thing as saying 2.5% decay. Okay, so let's go ahead and look at this first, our word problem. A car was purchased for $24,000. The function y equals $24,000. The function y equals 24 times 0.8 to the x power can be used to model the value of the car in thousands of dollars x years after it was purchased. Does the function represent growth or decay? Well, looking at this, 0.8, that's less than 1, so I know, hey, this one is decay. It's always going to be decay no matter what. What is the rate of growth / decay for this function? What does it mean? Okay, so my rate of growth or decay. Well, I can do the same thing as before. So 1 minus r equals 0.8, which is the same thing as just saying, hey, this is a 20% decay. Okay, what does that mean? So 20% decay means it is worth 20% less each year. But we know that that's how it works with cars. Like, as soon as you buy something, it loses value, okay? So that's just something that you need to know. Graph the function with a reasonable domain, and what is the y-intercept represent? So my y-intercept, I went ahead and gave you the graph of it just down below. The y-intercept, so here we can just answer this question down here, C. My y-intercept is the original price. So it's the original price. When there's no time that has passed, it is just what it is right then and there. Okay, last one, D. I want to skip this first question. I want to do the second one. What will be the value of the car in 32 months? Okay, so thinking about this, we have 24 times 0.8 to the 32 months. So this is, x is in years, right? Yeah, okay. So 32 months as years. So what is 32 divided by 12? Well, that's going to give me 2 2/3. So 2 2/3, which equals 13.24. So the actual real price is going to be $13,002. 237 if I were to do the actual like full amount. So I can take that, or you could say 13,240, somewhere around there. But if I want it to be precise, then I'm going to say 13,237. Okay. I'm going to go ahead and cut this video, and then I will put up a second one in a minute.